neuromuscular junction. Now look, I'm not going to ask you questions going back over resting membrane potential and action potential, guys. You just kind of, within the context of what's going on, we have to understand that it's action potentials that's coming that causes our muscles to contract. And if you think about it, skeletal muscles is the only thing that you have conscious control over as far as outward response. I'm not talking about your own thoughts. I'm not talking about that. Think about everything else. Everything else is autonomic. Everything else is on autopilot, right? The only thing that you have conscious control or subconscious control is your skeletal muscles. So I say subconscious because we do a lot of things out of habit. Like I have a tendency to talk with my hands, so I'm always using my hands when I'm talking. People told me I do expressions with my eyebrows and my face and all that kind of stuff. Whatever. All right, that's subconscious, right? But it's still I have conscious or subconscious control over that. Oh, so all of this is coming through from action potential down what type of neuron? What type of neurons are causing my muscle to contract? Motor neurons, right? Okay. And so you have one motor neuron is going to control a set number of muscle fibers. Okay. That's called whenever you have to say, it's called a motor unit. It's called a motor unit, right? Some motor units, all motor units have one motor neuron. All of them. Okay? But some motor units have more or less muscle fibers depending on what type of muscle it is. What's probably some of the strongest muscles in your body? Okay, for its size, your tongue. Okay, your butt cheeks, which are called your gluteus maximus. You also have your gluteus medius, right? Very powerful muscles. Your glutes are going to have, relatively for its size, fewer motor units, but each unit will have more fibers. Okay, they don't do a lot of detailed movement. All right, whereas muscles in your face or muscles that control your fingers, okay, that do a lot of detailed movement, those motor units are going to have kind of fewer muscle fibers per unit, okay, because they do a lot more different movements. All right, I forget what the number is, but there's it's been years since I've seen this. I want to say it's in the tens of thousands, but I may be exaggerating. Maybe it's in the hundreds. But your hand supposedly could do like hundreds or maybe even thousands of different combination of movements. And that's why people can and some people, of course, are more dexterous. That's why they're able to play the piano. If I could play the piano, I would have to be doing it this way. I couldn't do both at the same time, I don't think. I really don't think I could. So, anyway, I was not very musically inclined. My brother was very musically inclined. He taught himself how to play the guitar. He taught himself how to play the piano. Never took a lesson. Anyway, all right. So let's get on to some of this. All right, so we remember some of this: depolarization, repolarization, hyperpolarization. Okay, so neuromuscular junction. All right, so I'm going to draw some things up here. I'm going to erase a lot of that. All right, so neuromuscular junction. Neuromuscular junction, okay? Again, it's just where the motor neuron connects with the sarcolemma of the muscle fiber. Can you remind me what the sarcolemma is? So what?
Something like functional.
No, that's a sarcomere.
The lines?
Sarcolemma, and Aaron went too far off. He's sarcomere, sarcolemma. Sarcolemma is just the name of the muscle fiber cell membrane. That's all it is. That's all it is. Okay? So, when you have the motor neuron,
What was it?
thank you. All right, so when the muscle fiber nerve impulse comes down, right? Okay? The motor neuron, this is the presynaptic terminal. Y'all remember that term? Presynaptic terminal? The postsynaptic membrane is the sarcolemma. That's just what it is, right? Okay? So, when the nerve impulse, the action potential gets there, it's going to release, remember it's going to release the neurotransmitters. What's the name of the neurotransmitters? Starts with A. Acetylcholine. Acetylcholine. Okay, so this is kind of where the whole process begins. All right, so acetylcholine is going to cross the synaptic cleft. Okay, this is where we have to kind of know terminology. Okay, the context of terminology. So it's going to cross the synaptic cleft right here, this gap. It's going to bind to receptors on the sarcolemma of the muscle fiber. Of course, that's going to generate an action potential in the muscle fiber, causing it to contract. Now, what has to happen to acetylcholine as soon as it binds here? It has to break down. And what breaks it down? Acetylcholinesterase. All right, so all you're adding to this is sterase. ACE is telling you it's an enzyme. Okay, every time. All right. It has to immediately be broken down. Parts are reabsorbed. They're going to be reassembled. They're going to be repackaged, ready to be released again. So if you have a continuous stimulation, like I'm holding my arm up right here. So what muscle is holding my arm up? My deltoid. The reason that's happening is not because acetylcholine binds to the receptors and just stays there. It's because this process of being reabsorbed, repackaged, and released is happening in just microseconds. Okay? It's a rapid fire. And the rapid fire nerve impulse is happening so fast that there's no time for your muscles to relax in between. Okay? Now, certain muscles you keep in contraction all day long. How long could I do that, do you think?
Like 3 minutes, 5 minutes.
Yeah, I don't know. Probably not that long. Okay? I have my shoulder joints. Feel this. Put your hand right here. Feel that?
I can feel your shoulder.
Yeah, you feel the gravel in it?
Yeah.
If I do that for too long, it's like, it's not even my muscles, it's my joint starts weighing me down. Anyway. These muscles right here are not meant to stay in contraction all the time. However, muscles that hold your head up, muscles that allow you to maintain posture, they are meant to stay in constant contraction. Okay? And we're going to talk about those different muscle fibers here in a moment. Okay, so here comes the nerve impulse, right? Okay, so the nerve impulse comes, and here we get to the sliding filament mechanism. Now, again, your book also refers to this as cross-bridge cycling. Cross-bridge cycling, sliding filament mechanism. You also sometimes hear it as sliding filament theory, all right? So I guess maybe there is some theory behind this other than absolute knowledge. But here's what they believe happens, all right? So there's this, kind of mentioned it yesterday. There's this organelle in your muscle fibers called the SR. Does anybody remember what SR stands for? Sarcoplasmic reticulum. Going back, sarcoplasmic reticulum is that yellow lattice that kind of encompasses the cylinder of the muscle fiber. Okay? Now, SR is saturated with calcium ions. Okay? It's saturated with calcium ions. Ca2+. Alright? When your muscle fiber is stimulated by a motor neuron action potential, okay, all of a sudden the SR becomes permeable to the calcium ions. So what do you think the calcium ions are going to do? They're going to go in where? But it's full of SR. I mean, it's full of calcium. Yeah, it's going to leave. It's going to go from highest to lowest concentration. The highest concentration is inside the sarcoplasmic reticulum. So since it becomes permeable to it, now it's going to leave. All right? It's going to flood out. Okay? Now, if you look at a sarcomere, okay, now this is not a great representation of a sarcomere. It's just actually showing one little part of it. Okay? The two primary, and I'll get Jane's question in a minute, two primary protein filaments that make up a sarcomere are myosin, which is a thicker filament, and actin, which is a thinner filament. Here, the actin represents a twisted strand of pearls. In reality, myosin is a whole lot thicker, relatively thicker than that relative to actin. And it's because of the way myosin and actin react with one another is is why your muscles are able to contract. It's why the sarcomere is able to shorten with force, which explains why your muscles shorten with force. Okay? So calcium, all right, so here's some other parts of it. Now you're looking at just this part of this, right? Right here. Okay? So here's the actin. All right, and actin have two accessory molecules that's associated with it. You may or may not be able to read it from there. But these little red parts right here, that's called troponin. I also have heard it pronounced troponin. I've always pronounced it troponin. Okay? And then you see this thread right here, kind of outlining. That little thread is called tropomyosin. Now, it's not called tropomyosin because it's part of myosin, but it does allow something. Okay, so there's troponin, there's tropomyosin. Again, these are accessory molecules associated with the protein actin. On myosin, you have these little structures called myosin heads. The myosin heads are what's responsible for grabbing on to actin. Okay? Alright, they're responsible for grabbing on. Okay, so for right now, without calcium, nothing can happen. Your muscles are relaxed. So if your body was completely depleted of calcium, you would not be able to move at all. None. Okay, so you always have calcium in you, at least a little bit. Alright? Most of it's stored where? In your bones. Okay, so yes, it does give your bone strength, but you need it for muscle contraction. Okay? So the calcium leaves, and the calcium is going to form a chemical bond with troponin. Alright, when that happens, it unlocks a door. Calcium is the literal key to let this happen. So think about putting the key open and all of a sudden the doors slide open, like Star Trek or something. Alright? So when calcium binds to troponin, okay, that causes this thread molecule, tropomyosin, to kind of shift. When it shifts, it exposes binding sites or attachment sites, two different ways to say the same thing, on actin. Okay? Now, myosin is then going to bind to those attachment sites. But what does each myosin head need? It's actually going to be an ADP plus a P, which is actually its ATP, and the phosphate is going to leave. And when it leaves, it gives it the energy to be able to bind to the attachment site. It is then going to pull the actin toward the center. This is called the M line right here of the sarcomere. So this is one end of the sarcomere, this is the other end of the sarcomere. So it's going to pull it in this direction. It is then going to release, and before it can release, it needs another ATP. It needs another ATP. And when it gets another ATP to release, then the ATP is broken down into ADP plus P, and then it's going to combine to the next place. That's when the phosphate leaves, and it's going to repeat that. That's called cross-bridge cycling. Okay? Let me go through it again. What's the very first thing that has to happen? Very first thing.
Calcium has to be released.
Okay. Calcium has to be released, and that's stimulated by a nerve impulse, right? For my brain. Oh, look, muscle just contracted, right? So calcium has to be released, and then calcium has to bind to what? Calcium has to bind to troponin. Then what happens? Tropomyosin is going to shift out of the way, exposing what? Binding or attachment sites. I can't remember which phrase I used on the test. It's the same thing, right? Okay. Then what happens? The myosin head has to attach to it. But what must be used to do that? ATP. I don't care if you know the difference between ATP and ADP plus P. I don't care about that. Okay. ATP has to be used. ATP has to be used. It is then going to pull it in this direction, right? Then another ATP is used to cause it to let go, reattach to the next attachment site, and pull it again. Then another ATP is used. Now, guys, how many myosin heads do you think you have per muscle? Probably more than there are stars in the observable universe. Observable. There's a lot. Okay? This is why you have to eat. Okay? Now, as Americans, we tend to eat too much, right? We do. We eat way too much. We probably could get by perfectly fine with 2 meals a day. We really could. We eat way too much. I'm included. I'm definitely included. But you're breaking down glucose. One glucose molecule produces 36 ATP in aerobic respiration. That ATP is to do things like this. You all know it takes energy to just see. If you're just stood there perfectly still, nothing else going on, and your vision's working, you're using energy.
That's why you go blind.
Say it again.
You go blind when you're starving.
Because when you go blind when you're starving.
How long is it possible?
It's possible to fast 40 days.
Really?
Oh yeah. That's people have done that before. And theoretically, maybe possibly longer than that. Just depends on how much fat and muscle reserve they have.
Fast as in not eating at all.
Correct. Drinking water and fasting. If you're sure. All right. Okay. Hey, I'm not quite done. Shh. All right. So look. So watch this. Now, this cycle continues, and think about this. Think about the myosin heads as being fists or your hands, and think about actin as being a rope. Okay. If you're trying to pull something or pull somebody, from hanging off a cliff, you can't just do this, right? You got to do it over and over and over again, right? Is that right? Okay. Your hand is myosin head. Grabs hold. That takes an ATP, right? And you pull. All right. Now this one grabs hold. That takes an ATP for this hand and pull. But this hand has to let go, right? So it takes another ATP to have this myosin head let go, grab on, and pull again, right? And so until you get all the way up. This is going to happen until it gets to the end. This is going to happen until it gets all the way to the end of the actin, which is anchored at the Z disc. The Z disc is the boundary between one sarcomere and the other, but it's also where the actin is anchored. Okay? Think actin A, Z disc Z, A to Z, it's anchored. I don't know.
And this is all muscle contraction.
Yeah, this is muscle contraction. Yes, ma'am.
I'm confused where this is happening.
Where?
Yeah.
It's happening in your muscle fibers. Okay, so let's go back. Let's go back and look at the big picture. Okay? All right? All right, so this is one of your muscles. Just one. Could be a small muscle, could be a relatively big muscle. All right? Inside of that, you have these muscle bundles called muscle fascicula. A dozen or so of those make up a muscle. Each of those muscle bundles, the fasciculus, is made up of muscle fibers. So there's many muscle fibers in there. All right? Now, inside the muscle fibers are these myofibrils. Okay? Each myofibril is made up of repeating units of sarcomeres. That's where it's happening. Now, in reality, what you looked at just a minute ago was one of this. This is a small part of a sarcomere. According to this picture, it looks like that's the entire sarcomere. That's false. In one sarcomere, you're going to have, let's say this is a myosin. You're going to have several of these in one myosin. Let's say you're looking at down the edge of it. You know what I'm talking about, the end of it? You're going to have several myosin, and each myosin is going to be surrounded probably by around a half a dozen actin. But this myosin right here, let's say this myosin out here, will grab on to possibly the same actin, but then also other actins that are surrounding it.
Wait, so all of those that we just put over are in that part?
Yes.
Okay, there's
Yeah, there's more than you can count. It's ridiculous.
And they're in every single muscle.
Yes. Yes. All right. So what has to happen for your muscle? Like, all right, so I'm contracting. My deltoid's contracted, right? My deltoid's contracting. I relax it. So what has to happen for a muscle to relax? What do you have to do first? What?
To let go.
Say it again. You've got to get rid of calcium. The calcium must be actively transported away. Okay? Now, so for relaxation, calcium has to be actively transported away back into the SR. Now, this is active transport. Does that take energy? Yes, that takes energy. That takes ATP. All right? It takes ATP to actively transport it back into the SR. When that happens, what's the tropomyosin going to do? It's going to move back, covering the attachment sites or binding sites, and that's what's going to break the binding between the myosin and the actin. Okay? Now, the binding, when a myosin head binds to the attachment site on actin, that's called a cross bridge. That's why this is called cross bridge cycling. This is just cycling. Okay? Okay? All right? So that's cross bridge cycling. Now, what? So calcium has to be actively removed, actively transported back to the SR. It's going against the concentration gradient. That's why it's going to take ATP to do that. When that happens, tropomyosin slides back over the attachment sites. When that happens, cross bridges are broken, muscles are relaxed. Now, what happens in a muscle cramp? There's not, it can't get out, can't get back in there. So it's like in a muscle cramp, that muscle has run out of energy. Calcium is already out, or it leaks out, stays here. You don't have enough energy to actively transport it back in the SR, so there's nothing to break those cross bridges so your muscles lock up. Okay? How many of you have not got your tetanus shot in a long time or never? Okay, this is why you need to get your tetanus shot, because this will make you very sad if you got tetanus. Y'all know what happens in tetanus? The disease? Okay, all right. So, acetylcholinesterase is destroyed. All right, that's awful. I'll let know out. I'll get out at 9 o'clock.
Turn that down.
All right. Slow twitch, oxidative, fast twitch, glycolytic. And then in between, you have fast twitch, oxidative, glycolytic. All right. Now, obvious things about them. Which one contracts more slowly? Slow twitch. Right. Okay. All right. Here's other things about it. It's not only slow, it is darker in color. And there's a reason for this. All right. The reason it contracts more slowly is because there's different ATP aces that break down ATP. This one, the ATP ace breaks down ATP slower. And that's the reason it contracts more slowly. This just contracts twice as quick as slow twitch. All right, but here's the reason it's darker. It's more vascular, meaning more blood vessels, which means more access to what?
Oxygen.
More oxygen. And more oxygen is used for what type of respiration? What type of cellular respiration? Aerobic or anaerobic? Aerobic respiration. Okay? All right? Now, also the reason it's darker is because it has a lot of myoglobin, which is a kind of a reddish-brown pigment. What's myoglobin sound a lot like? Hemoglobin. What does hemoglobin carry? Oxygen. Myoglobin can temporarily store oxygen, which gives it greater access to utilize aerobic respiration. Okay? This is much, much, much more efficient because for every glucose that's broken down, all right, aerobic respiration, it yields 36 ATP. But here's the other thing about slow twitch. Slow twitch can utilize any nutrient. So it can break down amino acids, it can break down fats. In fact, if it gets to the point where you're breaking down fats, it actually yields over 50 ATP. You ever hit your second wind? Your second wind comes because all of a sudden you're starting to break down fat reserves, and now you have that little burst of energy. That's what's going on. Okay? Fast twitch, all right, it's lighter in color. 2 reasons. 1, not as much blood vessels, so it has less access to oxygen. Blood's a darker substance, right? And secondly, there's lots of glycogen embedded in the fast twitch muscles. What's glycogen made up of? Glucose, right? So it has quick access to glucose. But because there's less oxygen, what type of respiration is it? Okay? There's decrease, and it utilizes anaerobic respiration. All right? There's lots of access to glucose, but here's the thing. How many ATPs are yielded when you break down glucose in anaerobic respiration? Anybody know? 2. And the reason this is called fast twitch glycolytic is because it relies on glycolysis. That's the first step of a respiration. If there's no oxygen present, it doesn't go any further. This one's called slow twitch oxidative because oxygen's present and it goes in. It uses oxygen. Okay. This is why this is fatigue. This is fatigues much more quickly, and this one's fatigue resistance. This one is fatigue resistance. All right. Make sure that sounds right. All right. So there's probably a few other things. I'm gonna touch back over this again beginning of Thursday, and then I'll do a lot of review. Fast twitch oxidative glycolytic is just a balance of the two. They're called intermediate glycolytic.